minus the true mean value, sigma square. So here sigma is the standard deviation. Okay. So and we said that if you plot this curve, it is going to look something like this. This is your px and this is x. So this characteristic equation can be used to describe the behavior of a population. What is a population?
So it should be x minus x dash square minus, if I'm not wrong,
Which one?
right?
Yeah, yes, correct.
X minus.
Yeah, you are correct. Yeah. So, what is a population? Population is a large data set. It could be infinitely large. Okay. So the thing is, when your data become infinitely large, this mean can actually represent the true mean. That means instead of x mean, we can actually use x prime. Okay. So this is basically your true mean. So population is infinitely large. That is what it says. So if you want to know what is the probability that a measurement will lie within a certain interval, then you can find out that P, the probability that the measurement will lie between, let's say, x prime minus delta x less than equal to x less than equal to x prime plus delta x. Let's say you're talking about this is your x prime and this is minus delta x, this is plus delta x. So you want to know what is the probability that data is going to lie within this interval. You can find out by integrating px dx from x prime minus delta x to x prime plus delta x. So this is enabled by the normal distribution or Gaussian distribution, normal or Gaussian distribution. So typically, if you want to find out the probability, these are tabulated and these tables are given. Normal distribution tables are given, which I will show you in a while. But they are typically represented in a slightly different form where they define a parameter called beta. So your beta is x, that means a particular data minus the true mean divided by the standard deviation. Okay, so this is for any particular value of x. Now, if you use x equal to some x1, okay, a particular data point, then you can write z1 is x1 minus x prime divided by sigma, and this is your z variable. Okay, so instead of writing a particular data point minus the true mean divided by sigma, the whole thing is dumped into a variable called z variable. So now with this definition, new definition, this equation now takes a different form. So we have the normal distribution curve appearing as, if you want to know, let's say, this probability that the data is going to lie within certain interval. Let's say you say probability that the data is going to lie between minus z1 less than equal to beta less than equal to z1. So beta is indicating equivalent to your true mean. Z1 is indicating on the left side and right side. This can be written as 1 over square root of 2 pi. Basically, you change the variable x to beta and z. So you integrate from minus z1 to z1 e to the power minus beta square by 2 d beta. Okay, so you can notice that we have gone from the variable x to variable beta, and your x minus delta x and x prime plus delta x is denoted as z1 and plus z1 and minus z1. So now this instead of x, so you have z. So the new characteristic curve becomes, so you have px, and instead of x you have beta. So you can say that what is the probability that data is going to lie between minus z1 to plus z1. Okay. So if you look at this term inside the bracket, it is actually squared, and this curve is actually symmetric about the central axis. That means you can integrate, instead of minus z1 to z1, you can say 0 to z1, and whatever area that you get here, if you do 0 to z1, you get half of that area, so you can multiply by 2 to get the total area. That means you can write that P, that the data is going to lie between minus z1 to z1 will be equal to twice of 1 over square root of 2 pi into integration from 0 to z1 e to the power minus beta square by 2 dv. Okay, so this is the probability that the data is going to lie between minus z1 to z1. Now this table is actually available. Okay, so let me first write down some special cases, and then we'll go to the full table. Let's say, so I'm going to talk about in terms of both x and as well as z. So let's say this is x, px, and I have beta and px. So let's say I talk about the data that lie, so this is your x prime. Okay, so this is when x prime, x is x prime, your beta will be 0, right? So this is 0. And so if you want to know the probability that the data is going to lie between minus sigma to plus sigma, that means we are talking about the limit x prime plus minus sigma, right? So this is the boundary. Or if I write in terms of beta, so I basically would talk about z1 minus 1 to plus 1, right? When x is minus sigma, your z will be minus 1. When x is plus sigma, your z will be plus 1. So if I can make a table, right? So I can say my z1, then the corresponding x prime plus minus sigma, then the probability px, which is the area under the curve. When z1 is equal to 1, so you are basically having x prime plus z1 sigma, x prime plus z1 sigma. So let's say first I have plus minus sigma, that means z1 is 1. So I'm only talking about plus minus sigma or minus 1 to plus 1. Your probability, if you evaluate this integral, so your p minus z1 less than equal to beta less than z1 equal to 1 over square root of 2 pi minus z1 to z1 is equal to minus beta square by 2 d beta, right? So when z equal to 1, z1 equal to 1, so it is the minus 1, then equal to beta, and equal to 1. is 1 over square root of 2 pi minus 1 to 1 e to the power minus beta square by 2 d beta. If you evaluate this integral, this is going to be 0.6826, or in probability term, it will be 68.26%. I will come back to that, what it means. If Z1 is 2, then we have x prime plus minus 2 sigma. Then we get 0.9545, that is 95.45%. And if it is 3, then we get x prime plus minus 3 sigma. And here it is 0.9973, so 99.73%. So what we're saying here is that, let's say we have some large data set, right? Infinitely large data set, because we are talking about population. And we plot them in for x-axis you have the data points, and y-axis is the probability density function. That means each data, how many times it is occurring, right? This is basically indicative of frequency. So if you do, then if the experiment is properly conducted, then you get a bell-shaped curve, right? It's a normal distribution curve. Now, once I have the data, I am asking now, if I do one more measurement, right? What is the probability that my measurement is going to lie within plus minus sigma interval, right? So that probability is 68.26%. What is the probability that my measurement lies within x prime plus minus 2 sigma, right? That probability is 95.45%. What is the probability that my data is lying within plus minus 3 sigma interval? That is 99.73%. So as you can see that as you are increasing the tolerance, that is decided by this Z1, as you are increasing your tolerance, you are including more and more data, right? So ideally, if Z1 becomes very high, let's say above 30, then you would see that your probability will approach almost equal to 1. Okay, so that means your entire data set. But if you are very selective, you have certain requirement where you do not want the data to deviate too much, right? You are just want to get very accurate, then you see that your probability is going to be very, very small. Okay, so we'll now take up an example problem so that these things will be sort of better appreciated. So the first question that we're going to solve, I'm going to write down the question. So we have an example question. Say that the statistics of a well-defined varying voltage signal, the statistics of a well-defined varying voltage signal are given by the true mean as 8.5 volt and the variance sigma square as 2.25 volt square. Then the question is saying if a single measurement of the voltage signal is made, if a single measurement of voltage signal is made, determine the probability that the measured value will be between 10.0 and 11.5 volt. The question is very clear. There is a lot of data available to characterize a voltage signal, and based on some prior measurement, you know the population mean and the variance of that particular signal. Question is saying that if you do a single measurement of that particular voltage signal, what is the probability that that signal value will lie between 10.0 and 11.5? Okay, so this is the question. So how do you solve this? First, so we note down that we know the true mean, which is 8.5 volt, and we also know the variance, which is 2.25 volt square. So from there, we can find out the standard deviation, which is basically square root of 2.25. That is 1.5 volt. Okay. So we have the mean, true mean, and the standard deviation. So we just want to know, if you want to read the probability table, then you have to find out the value of Z1. Okay. So we have seen that by definition, Z1 is basically x1 minus x true mean divided by sigma. Now, in this particular case, we first talk about the lower limit of the signal, that is 10.0. So we say that first we find the probability that the data is going to lie. If I draw here, so the data is going to be like this. So this is your x prime, which is 8.5 volt, and it is saying that what is the probability that data is going to lie between 10.0 volt and this is 10.0 volt, and this is here is 11.5 volt. So the probability table is listed as the area between the mean and a particular value, right? So first,
Professor,
yeah.
Sorry, how can you able to it is in the plus limit? Why it can't be the 10.75 can be the mean in this case?
Which one? Sorry, can you say again?
No, how can you? We don't know the limits, right? The constraint limits.
Yeah, so it says that the true mean is 8.5 volt, right? So this is where the true mean is.
Okay, okay. So
Then the question is asking that what is the probability that data is going to fall between this? Okay.
yeah, understood.
So
Got it. Got it.
the limits are 10 point volt and 11 point volt. So it wants you to find this area essentially. Okay. But the way probability table is listed is that you have to get the area between the mean and that particular value. Okay. So what we have to do is we have to find the area from here to here and minus the area from here to here. Okay. So first we are going to find the probability that the data is going to lie between 8.5 to 10 volt. Okay, so that is what we are doing. So x1 is 10.0 minus 8.5 divided by sigma is 1.5. So this will give you the value that is 1.0. Okay. Then we go to the probability table. Now I'm going to show you this table. So this is called the normal distribution table. Are you able to see this screen?
No, Professor.
Okay. Let me unshare and let me share my entire screen. Okay. So now you are able to see this table.
Right.
Right, sir.
Yeah. So if you look at the table, this is how the normal distribution table looks like. Okay, so you can see this equation I wrote, right? So this is the probability density function we wrote. So if you see the column, I'm sorry, different rows shows the value of Z1. That is your particular data minus the true mean, okay, divided by sigma. So these are listed here. The second digit after decimal is listed as different columns. Okay, the rows are up to the first decimal, first digit after decimal. The second decimal is here. Now our Z1 is 1. Okay, so you go here and we have like 1.00 basically. So our probability that the data is going to lie between 8.5 and 10 is basically 0.3413. Okay, so we read that from this table and we go there and we note down that from normal distribution table, we get that the probability that the data is going to lie 8.5 less than equal to x less than equal to 11.5, or the probability that is going to lie between -1 less than equal to the Z1 less than equal to 1 is going to be so this is not Z1, this should be this is going to be 10 to that, right? So this will be basically for corresponding to a particular Z1. So Z1 equal to 1 is basically point 0.3413. Okay, so this is the probability that the data is going to lie between 8.5 to sorry, not 8.5 to 11.5, we said 10. 8.5 to 10.0. That means this area here between these two, this. Now, if we subtract that from the area bounded by this line and this line, then we will get our target area, right? So we define Z1 for the second case where the data is 11.5 minus 8.5 divided by 1.5. So Z1 is basically 2.0. Okay. So then we can find probability that the data is going to lie between 8.5 less than equal to x less than equal to 11.5, or the probability corresponding to Z1 equal to 2 is, we have to go to the table. Okay, so if you go to the table, so you go 2.0 here, 2.00. So this is 0.4772. Okay, all of you can read here 0.4772.
Sir, what is the significance of the other columns?
So let's say, I mean, we got here instead of 1, we got 1.15, let's say, right? So we go here and we 1.1 and we go and we read this value here. Okay.
Oh, yeah. Okay. Okay, got it. Yeah, sure.
Because this is the second digit, the decimal.
Also, the Z is just a notation, right? I can say Z1, Z2. It's not a.
Yeah, you can say. I mean, this is see we we say that, I mean, why we are saying Z1 is that we are basically referring with respect to the mean. So, I mean, it is a notation. You can use Z2 also. It doesn't matter really.
Noted, sir.
So you can say that this is 0.4772.
Sir,
Yeah.
I seem to have missed it, but I didn't understand how we are getting into understanding the decimal, sir, from the table.
Okay, let me tell you once more. So you find out this Z variable. Okay. So you find out the Z variable by using this formula here. Okay. This is the data point. This is the true mean. Okay. So basically, you take the difference, divide by the standard deviation, and you get the Z variable corresponding to this Z variable. You can read the table and get the probability that the data is going to lie between the true mean and that particular data that you are talking about into 10 and 10 volt. Okay, so you go to the table, we get Z1 equal to 1.0. So here these different rows here indicate the value of Z1, right? So, and this different columns signify the second digit after decimal. So here Z1 is 1.00. So you go here 1.0, 1.00. So you get 0.3413. Similarly, in the second case, you found your Z variable happens to be 2.0, right? So you go here and you go to your Z variable. This is 2.00. So you read 0.4772. Okay. Now, what is
Sir,
So,
yeah?
sir, in case Z value is negative, we'll be doing the first.
So you basically take the magnitude because this is a symmetric curve. Okay. So you take the magnitude and you go there and read whatever is the positive value.
Okay, sir.
Okay.
and that decimal, what is there in the first row, that is a factor, that is kind of like an accuracy that we want to reach, right? It is-
Yeah. I mean, this is basically the first significant digit after decimal. But if you get, let's say, 1.456, right?
Okay.
You only
Yeah.
go to 1.45. Okay.
Okay.
You can do interpolation. Like, for example, you get 1.456, you can get 1.45, then 1.46, and you can interpolate.
Okay. It's like that. Okay.
You get my point, right?
Okay.
So now, what is this probability signifying? It is signifying the area under the curve from here to here. Okay, so how do I get this area? I subtract this from that, right? Then I will get the target area. So the probability that, I'm just using space here, the probability that the data is going to lie between 10 and 11.5 is going to be the probability corresponding to Z1 equal to 2 minus probability corresponding to Z1 equal to 1, and which is 0.4772 minus 0.3413. We got this as 0.1359. So that is, there is a 13.59% probability that if you do one more measurement of the voltage, it is going to lie in this range between 10 and 11.5. Okay. So, I mean, you can, depending on the question, it's just the procedure is basically the same. And if you understand, your data with respect to the mean, then you can work out and read your probabilities. Okay, so talking about this probability, you can see that I was saying that as you increase Z, right, you are basically spreading your interval. You see that the probability is going up slowly, and you can see that at about 3.09, it is reaching very close to 98%. If you go to higher Z, sometimes it will become 0.5. That means you have reached nearly 100%. You have covered all the data. Okay. So this table, I mean, you can download it. If you need, I can share with you also later for your reference.
Sir, one query I have. Suppose, let's say the question asks that suppose we measure two points.
Yeah.
And find out the probability that where these 2 points will lie with respect to mean in that. So in the first case that we have taken is like x1 minus x bar, and we have deduced that. For the second point.
No, I didn't get your question.
My question is, sir, suppose the question asks is single measurement, na?
Mm-hmm.
Suppose if someone asks that two points were measured, and what is the probability that 2 points will lie with respect to mean? So for
the 2 points will lie within this interval.
Yeah. Or with respect to mean, whatever.
Yeah. So when you say 2, then you have to use the formula, the probability formula. So you have to find the probability for the first point, then you have to find the probability for the second point, then becomes whether and or, right?
Okay.
When you say and, then you multiply the probabilities. When you say or, then you add the probabilities, right? So that is typically the basics of probability. So you find individual points, and then you work on simple probability theory to find out. Is that clear to you?
Yes, sir. Yes, sir.
Okay. So we move on and talk about statistics of a finite size data set. So here we talked about we talked about true mean, and true mean by definition assumes that it is an infinitely large data set. Otherwise, your mean can never be true mean, right? So now we talk about statistics of finite size data set.
Sir, may I ask one more question if you allow, please?
Yeah.
Request. So basically, in last class, you have told that px is equal to limit delta x tending to 0 and j divided by n to delta x.
Yes.
So if the data set is data is very large, and the delta x is approaching 0, in that case, the probability function will become a normal distribution curve. And the sigma was like brought in the picture.
Yeah.
Now, sir, what is a mathematical, I would say, like expression for sigma? Like what I mean to say is, why this has come in that way? Like, what is the?
How do you find sigma?
Yes, sir, yes, sir.
Yeah. Come to that. I mean, we are not very far from actually working with the data points and finding out sigma. So you find the mean, and then from the mean we are finding. I'm just going to come there.
Okay, right, sir. Thank you, sir.
Today we'll talk about sample variance, but from the sample variance you can find the population variance and so on. So we are coming to that slowly.
All right, sir. Okay.
So today we'll talk about statistics of finite data sets. So we have about some 8 minutes we have, but we'll try to finish as much. So the thing is, the finite size data set, typically your n is less than 30, and when n becomes greater than 30, we say that large data set. So the thing is, you are trying to predict the behavior of the population by doing measurements by doing a small set of measurements in the form of sample, right? As I was saying, like, if a company is manufacturing bearing and you are trying to know what is the diameter of the bearing that the company is manufacturing. Okay, so that means you are talking about, let's say, over 1 week or 1 month, the entire population. So which is impractical to do. So what you do really is pick, some 10, 20 or 50 or whatever, and then you measure the mean and standard deviation and you extrapolate that to the population. You say that, okay, I mean, the diameter of all the bearings is between X plus minus something, right? So that's from that angle, the finite data set becomes important. It is very relevant from practical point of view, right? So you basically do sampling, okay, and from sampling you basically try to estimate the true mean and variance or standard deviation of the population. Okay. So as I said, you pick, let's say, 20 bearings and you measure the diameter. So you basically have n repeated measurements. N can be 10, 20 or 30. So n repeated measurements of the variable x. That variable x is, let's say in this case, the diameter of the bearing. Now, when n becomes infinity, right, you are talking about the infinite statistics. And where you talk about true mean and variance of the population. And when n is finite, you basically talk about the mean and variance of finite data set. Okay. So how do you, when you do n repeated measurements, how do you find the sample mean? So you find the sample mean using this formula. So you say the sample mean is basically sum of xi, okay, I equal to 1 to n divided by n. Okay, so that is how you find the mean of your sample. How do you find your variance or standard deviation? Your standard deviation for the sample, the standard deviation is indicated as S subscript X, not sigma. Sigma is the population standard deviation. And the data set is very, very large. For a finite data set, you indicate by symbol Sx, and that is equal to 1 by n minus 1 sum I equal to 1 to n xi, the data set, individual data, minus x mean square with the square root of that. So that is how you find out the standard deviation of a finite data set. Here you can notice that it is n minus 1, okay, not n. So this n minus 1 is indicated by nu, which is called degree of freedom. So I will come to that, what we mean by degree of freedom. In a data set, the degree of freedom nu is, particularly when you calculate standard deviation, it is taken as n minus 1, the number of data points minus 1. Why? The degree of freedom basically is understood as follows. It says that if you have n number of measurements, right? So you have n different data points, independent data points, right? You have n independent data points. But then when you calculate standard deviation, you are using one variable here, that is the mean, which is calculated again from the data set. Okay, so the degree of freedom is basically defined as number of independent scores of data minus number of parameters used as intermediate steps in the estimation of the parameter itself. That means the parameter that we estimate is standard deviation, number of independent data points is n, but while estimating standard deviation, we are using one parameter, that is mean, which is estimated from the data set itself. So this -1 is basically for x-mean. Okay, so that is why for a finite data set, you have to use n-1, okay, as the degree of freedom. So this degree of freedom you should remember, because we'll use this as a the table for finite data set. Now, I talked about the the normal distribution table. Okay, when you the normal distribution table is read when the data set is very large, but we call T distro. Okay, so if you see this table here, it says normal distribution table or Z distribution table, but we will see that for a finite data set, so to use T distribution table, because the normal distribution table with finite data set will give you erroneous results. Okay, so how normal distribution and T distributions are different? Okay, so let us talk about that. So typically for finite data set, you would write that your data point xi is going to be x mean plus minus t, a variable which is a function of degree of freedom and probability, into Sx, and this is considering p% probability. Okay, so you can really say that if you have a infinite data set, then this t is replaced by z. Okay, when it is for infinite data. Infinitely large data set. So if you look at the characteristics, this is the normal distribution curve. Okay, and when you have small data set, typically you get a curve which is not flatter, something like that, and this can be, let's say, your degree of freedom equal to 5. As you go to a slightly higher degree of freedom, maybe it can become something like that. Okay, so this can be, let's say, degree of freedom is 10. That means here your data is 6, here it is 11. And when you go, your degree of freedom is very large, right? Infinity. So typically degree of freedom greater than 30, you get a characteristic curve which is same as the normal distribution curve. So this is normal distribution curve. Okay. So what this t variable, how do you actually define this t variable? So this t is basically defined as follows. So t is taken as the mean of the finite data set minus the true mean divided by the standard deviation of the finite data set divided by square root of n. Okay. So now if I draw the characteristics of the t distribution, this is ft and this is t. We said this is going to be relatively flatter compared to the normal distribution curve. So you say if you want to know that, okay, what is the probability that a measurement will lie between the central value, that is your x mean, and t nu p, that will be the area under this curve. Okay, and so this will be the probability that the data is going to lie between x mean and t mu p, and the probability that the data is going to lie outside that is basically going to be 1 minus p. Okay, and like normal distribution, t distribution is also symmetric, so that means you have basically whatever t mu p, if you go t minus t mu p, you will have the same area. So typically, even in small data set, your n has to be greater than or equal to 10, and if n is smaller than 10, typically, the data, the results that you get could be, the statistical analysis that you do could be misleading. So let me now talk about one more thing before we stop. We talked about, we really want to understand the population, right? But we cannot really measure the population. We cannot get data for the population. It is impractical. So what you do is a sample. That means you pick a small data set and you measure mean and standard deviation. But you really want to understand the population, right? So how do you really predict the population correctly from the sample? If you let's say we have taken n data points for the sample, okay, and we get our x mean and standard deviation. Let's say you picked some 20 bearings and you measure the mean diameter and standard deviation. Let's say you pick another 20 from the lot, right? And you may get some other mean and some other standard deviation, right? And if you keep on picking similar data set, each having n measurements, let's say you carry out m different data set, each data set containing n different measurement. Each data set has a mean, right? x1 mean, x2 mean, and the corresponding standard deviations, right? Statistics says that these mean values of individual data sets, m number of data sets, will also follow a Gaussian distribution. Okay, so that means if I get x1 mean of first 20 bearings, x2 mean of next 20 bearings, and then let's say I do 10 such data set, each having 20 bearings, and if I take the mean of each of these data set, these means are also going to follow a normal distribution. Okay, so that means, let's say the first mean could look something like this, the second mean could look something like this, the third mean could look something like this, Okay. So the first mean looks something like this. So what it says that these mean values of each of these are going to follow some kind of standard deviation curve. Okay. And so if we find the standard deviation of these means, that means like we had x1, x2 up to xn, we found the standard deviation of the data. So now we have x1 mean, x2 mean up to xm mean, right? If you find the standard deviation of this data set, x mean, then the standard deviation of the means of individual data sets, m data sets, is going to be the standard deviation of a given data set divided by square root of n, number of data sets in each data. So what it says is that by picking only 20 bearings, by only doing one sample data set, you will be able to predict the standard deviation of the means of all the data sets had you done that measurement. But you really don't do. But if you do, then the standard deviation of the means of all the data set happens to be Sx divided by square root of n. So I will stop here, but I will continue this tomorrow, so that we start from here again. Okay, so let us stop, and if you have any question, let us discuss.
Thank you, sir.
One question that I have, sir, like you told that n samples that we have, right, sir?
Yeah.
And x1 bar, x2 bar, and x3 bar to xm, like we have done the measurement in that.
So x1, I said that in each data set contains
Yes.
n different data points, you have a mean which is indicated by x1 bar.
Exactly.
And pick m number of such data sets. Okay, so that means these means also exhibit a standard deviation, a normal distribution trend. Okay, right?
Okay.
Mean value of each data set, each of these m different data sets, will also exhibit a normal distribution trend. Okay, so then if they exhibit normal distribution trend, they will also have some standard deviation, as I said here. Right? They will also have some standard deviation. Now, I'm saying that this standard deviation can be predicted by just doing only one measurement, one data measurement, and dividing it square root of n. So this is according to statistics. Okay, so people have come up with this correlation that if you do only one measurement and you know how many data points are there in that data set, you can predict the standard deviation of the means. Okay.
Okay, sir. Okay.
Yeah. So then you can really, I mean, instead of using a Sx here, you are going to use a Sx mean, and that is actually a better way of doing statistical analysis than using just Sx. Okay, so this is something that we are going to talk about tomorrow. So let us wait.
Right.
Thank you, sir.
Okay.
Thank you.
Thank you very much.
Thank you, sir.
Thank you, sir.